0. When m is not equal to n, this goes 0. But either way, in both cases, the right-hand side is 0, and therefore this integral equals that integral. Okay? And that's going to put constraints on what this a hat, this operator, can be. Right? So, writing it out. So if the difference was 0, so this integral must equal that integral. Now, in general, now in this case, these functions here are eigenfunctions, right? But in mathematics, we'll generalize. Now, forget quantum mechanics for the moment. Just think ordinary math. Just think math. Now, if you have two functions, phi and psi, and this is psi and phi. Now, if this equals this in general, where these are just general functions, now this is not quantum mechanics now, just ordinary math. So if you have something like this in mathematics, just between two functions like this operator here, a, if this is true, that operator is special. Oops, I've left out the hat. Okay. So if the operator satisfies this property, that this integral equals that integral of that form, that operator is given a special label. It's said to be Hermitian. Hermitian, that's from the French mathematician Hermite, or Hermite, if you anglicize it. We've met that name before in the Hermite or Hermite polynomials in earlier lectures when we were solving, what was it? Was it the simple harmonic oscillator? I think so. Okay, all right. Now, okay, so now that's in general. Now, so a particular kind of functions here are the eigenfunctions. So that means these operators here, in the context of quantum mechanics, obey this. So that means that these quantum mechanical operators are Hermitian. Okay, and that's an important property on, like a constraint, if you like, on the nature of quantum mechanical operators. So if you're going to have an eigenequation like this in quantum mechanics that has this property, and you want the constraints that the eigenvalues have to be real, and your eigenfunctions here have to be orthonormal. That's each of these constraints you're imposing on your eigenequation. Then this operator here, your quantum mechanical operator, it has to be Hermitian. Okay? So it looks as though, so if our assumption that quantum mechanics, for each observable there is an eigenequation, then it looks as though we can conclude that for each observable there is not just an operator, there's a Hermitian operator. Okay? I'll say that again because we'll meet it again and again and again from now on in quantum mechanics. To each observable, in other words, each physical measurable quantity in physics, there corresponds, in quantum mechanical theory, there corresponds a Hermitian operator. And you use that Hermitian operator in an eigenequation, okay, of this form, and the eigenvalues you get when you solve this equation, this eigenequation, those eigenvalues correspond to the measured values of the observable you're talking about. Right? So, it's a big idea. All right? Now, we can go the other way. Right? So, I mean, think about it. What did we do here? We made the assumptions that the eigenstates are orthonormal. We also made the assumption that the eigenvalues are real. And put those two assumptions together, and we deduced that these operators here must be Hermitian. Right? Hermitian just means that the operator satisfies this property here, that this integral equals that integral. Now we can go the other way. We can say if the operator is Hermitian, then the eigenvalues are real and the eigenfunctions are orthogonal. Okay? We can go the other way. So in a pure mathematical term, it's an if and only if. If you followed my previous course on finite group theory, we did lots of proofs of the type if and only if. In other words, you start with the right hand side and you prove the left hand side, or you start with the left hand side and you prove the right hand side. You go both ways. So it's a two-part proof. Well, here's another example. Okay? So this time, if we assume that the operators are Hermitian, we can conclude that the eigenvalues are real and the eigenfunctions are orthogonal. Now, I've run out of board, but I can give you half of that. I can actually prove to you that the eigenvalues are real. Right? So I'll prove that now. Now, the logic gets fairly tight, right? It becomes algebra after a while. And I'm going to use the bracket notation. Not this clumsier integral, overlap integral type notation. It's just more compact, but you need to think a bit, right? Okay. So what do we? Yeah, I can almost put this in a mathematical format, like theorem, proof, right? So the theorem is the eigenvalues of a Hermitian operator are real. Right? That's the theorem statement. And now follows the proof. Okay? So, alright, so let's rewrite. Now this is in overlap integral format, in the integral format. So let's rewrite this in terms of the bracket, Dirac's bracket notation. So now instead of having psi and phi, we're just going to have the same function. So we'll just talk about phi. Phi and psi. So we'll just have phi and phi. Okay. Now that means you can rewrite this in the bracket notation as phi. So here the same phi and a phi, because we're using the same function. Okay. So a phi. Here it is here. Bracket. Okay. Now. What have we done here now? Oh, I see. Now this is this. Okay, so now let's and instead of psi, again we'll have phi. So we'll phi a hat, phi star. All right, so translate this into bracket notation. So this will become phi star. Can you see? If you have like star, that would be just phi. And so if you put that in bracket notation, you get this. Right? So a hat phi star. Now the overlap integral, the first function here is usually starred. Okay, so if you star, do it twice. That's why you get a phi star here. All right, so that equals that. Now, in general, an earlier session, a few sessions back, when you use the bracket notation, the bracket of xy starred is equal to the bracket reversed. So xy starred is yx. Okay, we did that. I don't know, 3, 4, 5 sessions ago. Okay. So we're using that. We're using that here. So if you take these two and reverse them, that's the equivalent of conjugating it. Okay? So if I conjugate this and reverse it, I get the same thing as when I started. Alright? So conjugate it and reverse it. So if I conjugate this, I'll just get A hat phi. But it's on the left hand side now because it got reversed. And if I conjugate this, I'll get phi star star and then reverse. So that's where this comes from. Okay, I hope you follow that. It's just algebra now, but pretty dense reasoning, so you need to pay attention. All right. Okay, now you can rewrite, so that equals that equals that. Now you can rewrite this by using the eigen equation. A hat phi is just lambda phi. Okay, that's from here. A phi is lambda phi. So this ket here, you rewrite as just lambda phi. Okay, now lambda is just a complex number, let's say, well, just a number. So it's just a scale. So you can bring this out the front here. So then you've just got phi phi. Okay. Now we can rewrite this as now a phi from the eigen equation. A phi is lambda phi. Right? But we're conjugating the whole thing. So we'll get lambda star phi star. Right? That comes from here. That's what this arrow is about. All right? Now again, this is just a scalar, just a number. So bring it out the front here. So then you've got phi star, bracket phi star phi star. That comes from here. But this is now if I reverse these two, that's the same thing from here. That's the same thing as just conjugating it. Okay. So if I conjugate and reverse, I get the same thing as what you started with. So this bracket is just the same thing as phi phi. Follow that reasoning? Okay. Well, that then means now that equals that equals that equals that. They're all equal to each other. So that means that this is equal to this. Okay. So that implies that lambda equals lambda star. And star just means conjugated. So if you conjugate a number and it's equal to that same number, that number is real. Okay? So if lambda equals lambda star, then that means that lambda belongs. This symbol here is like it's a capital R with like two verticals. That's the symbol in math for the set of real numbers. So that means lambda belongs to the real numbers. In other words, lambda is real. Okay? So assuming that your A hat is Hermitian, in other words, this is true, and if that's true, then that is true. Okay? Assuming that A is Hermitian, we have now proved, that's the end of the proof, we've proven that the eigenvalue, lambda here, belongs to the reals, that lambda is real. Okay? Now, I've run out of board, but like the second part of that proof, not this proof, but the second part is if your operator is Hermitian, then not only are the eigenvalues real, but the eigenfunctions are orthogonal. So we'll do that next session, because no more board. So, ciao.